You know, we use them every single second of the day, but we hardly ever stop to think about how they actually work. I'm talking about computer networks. Today, we're going to pull back the curtain and demystify the very first steps that let data travel from, well, anywhere to anywhere. So let's dive in. Seriously, have you ever really thought about it? How does your phone, probably the one you're watching this on right now, talk to a server that could be thousands of miles away? A simple tap, and a video appears from another continent in seconds. I mean, it feels like magic, right? But it's not. It's just a brilliant step-by-step process. And today, we're going to tackle the first two most fundamental steps of that entire journey.
So, at the very heart of it all, you have the computer network. And honestly, the best way to think about a network is to just imagine it's the world's most efficient postal service. It's not just one mail truck or one post office. It's the entire system. The roads, the sorting centers, all the delivery routes. Everything working together perfectly to get your letter, or in this case, your data, exactly where it needs to go.
All right, so let's get into Unit 1. This is all about the absolute basics, the physical stuff. Because before we can send a single digital letter, we need roads. We need a physical path for our data to travel on. This is where we lay down the digital highways.
Now, these digital roads, they basically come in two main sizes. First up, you've got your local area network, or LAN. Think of these as the local streets in your neighborhood, connecting everything in your home or office, your computer, your printer, your smart TV. Then you have the big one, the wide area network, or WAN. These are the massive highways that connect entire cities, states, and even countries. The internet itself, that's the ultimate WAN.
Okay, so just like a city needs a plan, a street grid, some kind of logical layout, a network needs one too. In the networking world, we call this layout a topology. It's basically the map that determines how all the devices are connected, and it has a huge impact on how well our data traffic is going to flow.
The simplest design, the most basic one, is the bus topology. Just imagine one long main road. All the houses, or in our case, all the devices, connect directly to that single road. Now, it's super cheap and easy to set up, but you can probably see the problem, right? If there's a break anywhere in that main road, the whole street gets cut off. It's a massive single point of failure. So a much more reliable and common design is the star topology. In this setup, every single device connects to a central point, like a hub or a switch. Think of a town square with all the streets radiating out from the center. The advantage here is pretty obvious. If one road gets blocked, all the other roads can still reach the town square. It's just way more robust. So what are these digital roads actually made of? Well, we have a few options. There's the twisted pair cable. That's your standard copper wire, like an old phone line. Think of it as the common city road. Then you've got coaxial cable, which you've probably seen for your cable TV. It's more shielded, kind of like an armored transport route that protects the signal. And then there's the Rockstar, fiber optic cable. This thing uses pulses of light to transmit data. It's the high-speed light rail of the data world. Insanely fast, incredible bandwidth. Okay, so our roads are built. That brings us to Unit 2. Now we need to talk about what actually travels on those roads. See, you can't just throw raw data out onto the highway. It has to be properly packaged and addressed, just like a letter before you put it in the mailbox. And this is where things get really, really clever. This whole packaging process happens at what we call the data link layer. Now that might sound technical, but just stick with our analogy. If the cables are the roads, the data link layer is your local post office. Its main job is to take your raw message and prepare it for the very first leg of its journey. So how does this digital post office actually work? Well, it uses a process called framing. First, it takes your big message and breaks it down into smaller, manageable chunks. Then it wraps each of those chunks in a digital envelope. This envelope gets a header and a trailer, which includes the local to and from addresses. And this complete package, the data plus the envelope, is now officially called a frame, and it's ready to go. But, a good postal service doesn't just send letters, right? It makes sure they arrive safely. And that brings us to the next part of Unit 2, the quality control that happens at this stage to make sure we get a reliable delivery. I mean, how do you know if your digital letter got crumpled or torn on its journey? Through something called error detection. A really common method is the cyclic redundancy check, or CRC. Think of it like this. Before the frame is sent, the post office does a quick calculation and creates a unique digital fingerprint for it. When the frame arrives, the person receiving it does the exact same calculation. If the fingerprints don't match, they know the data got corrupted along the way and they can ask for a new copy. It's pretty brilliant.
And finally, there's something called flow control. You can't just dump a million letters on someone's doorstep all at once, right? The simplest way to manage this is called stop and wait. You send one frame, you wait for the "yep, I got it" confirmation, and then you send the next one. It works, but man, is it slow. A much smarter method is the sliding window. This lets the sender mail out a whole batch of frames at once. As the confirmations start rolling in, the window of what it's allowed to send slides forward. It is just way, way more efficient.
So let's just take a step back for a second. We've covered the physical roads and the local post office. It might seem kind of basic, but these foundational steps are absolutely critical. They establish the rules of the road for every single piece of data that crisscrosses the globe.
So, if you're going to take anything away from this, remember these key things. First, the physical stuff, the cables and the layout, creates the roads. Second, the data link layer is that local post office that neatly packages your data into frames or envelopes. And third, all those important checks for errors and flow control make sure those envelopes actually get delivered reliably. Seriously, without this groundwork, nothing else in networking would even be possible.
Which brings us to our final thought, and a really big question. Your digital letter, your frame, is packaged up. It's addressed for its local trip, and it's been quality checked. It's sitting there at your local post office, ready to go. But how does it get from there to a completely different network, to a different city, or even a different country? How in the world does it navigate the entire global postal system? Well, that's a question for the next layer. Thanks for tuning in.